Good morning, students. Welcome to lecture number 20, Inspection and Defects in Sheet Metal Forming. The objective of this class to understand the defect and remedies of sheet metal forming processes. You can see the terms like friction bulge test, nesting of blanks, tearing and buckling control, notches to avoid wrinklings, stress concentration near the bends in this class. So if we want to talk about all these terms, it is important for us to understand the term called as formability of sheet. That is, if the sheet is unable to form properly, normally defects will arise. Sheet metal formability is generally defined as the ability of a sheet to undergo the desired shape change without failure, such as necking and tearing. So you can see over here, okay, so it has been teared into pieces. Here also the tearing has been happened. Here you can see the edges of the sheet are not perfect. And so these all are some kind of issues or issues which normally relates to the formability of sheet. So the main three factors which influence the formability of sheet is, first one, the properties of the sheet metal. Second one, friction and lubricant at various interfaces in the operation. Characteristics of the equipment, tools and dies used. We will discuss these things in the details in the coming slides. So first we will see about the properties of metals or characteristics of metals important in sheet metal forming operation. The first and the foremost point which is mentioned here as elongation of the sheet. So it determines the capability of the sheet metal to stretch without necking and failure. So high strain hardening coefficient N and strain rate sensitivity exponent M are desirable. I hope N and M you might have studied in material science also, where you are relating your actual stress and strain values. The next term is yield point elongation. So yield point elongation, there is one defect which comes into the sheet normally known as the Luder's band or stretcher strains. I'll come to it later. Anyhow, just for understanding, we'll see that it is typically observed with mild steel sheets, okay, in which flame-like depressions on the sheet surface. You can eliminate this by timber rolling, but sheet must be formed within certain time after rolling. So I will explain this in the coming slides. Next property is anisotropy. Anisotropy is in two types. One is in planar, other is in normal. So planar anisotropy means exhibits different behavior in different planar directions, present normally in cold rolled sheets because of the preferred orientation in mechanical fibering causes earring in deep drawing, okay, can be reduced or eliminated by annealing, but when you go for annealing, it lowered the strength. So anisotropy planar is normally a defect. With anisotropy planar will normally occur in the case of cold rolled sheets because of the rolling direction will stretch or enhance your what I can say, the grain orientation will changing. So it is getting stretched, as a result towards one direction or the direction on which it is rolled, you are going to change the properties. That is, different planar directions properties are going to change. So you can reduce it by going for annealing, but you have to compensate on the strength. Now anisotropy normal determines thinning behavior of sheet metal during stretching it has to be taken care in the case of normally deep drawing operation. The next one which you have to taken into account is grain size. Determines surface roughness on stretched sheet metal. The coarser the grain, the rougher the appearance. Okay, the coarser the grain, the rougher the appearance. Also affect material strength. So proper grain size sheet also you have to take for forming. Next one, residual stress. So typically caused by non-uniform deformation during forming, results in part distortion when section can lead to stress corrosion cracking, reduced or eliminated by stress relieving techniques. That is on the case of rolling operation, or in the case of other manufacturing operation, some energy is stored inside the material, that is normally called as the residual stresses. Next one is spring back. We have already discussed the spring back in the details in the last class. Due to the elastic recovery of the plastically deformed sheet after unloading causes distortion of the part and loss of dimensional accuracy. Can be controlled by techniques such as overbending and bottoming of the punch. So using these things, so this is the overbending is a normal technique which is used to overcome the spring back effect. Next one is wrinkling. So wrinkling is caused by compressive stress in the plane of the sheet, can be objectionable, depending on its extent, can be useful in imparting stiffness to parts by increasing their section modulus, can be controlled by proper tool and die design. That is, if you are forming it and if the forming is not uniform, you can see wrinkles may obtain on the flanges as well as on the side walls of the deep drawn products. Now the quality of the sheared edges. So depends on the process used, edges can be rough, not square and contain crack, residual stresses and a work hardened layer which are determined to the formability of sheet. So this work hardening coefficient we are discussing here. So strain hardening or work hardening coefficient N. Okay, so that is has to taken into account. So formability of sheet, edge quality can be improved by fine blanking, reducing the clearance, shaving and improvements in tool and die design, and employing lubrication also. Quality of sheared edges you can improve. As a result, your final product you will obtain without any defects. The last one, surface condition of sheet. So depends on sheet rolling practice, important in sheet forming as it can cause tearing and poor surface quality. So from this you will get an understanding about the various defects which are directly correlated directly to your metal sheets, whatever you are using for your sheet metal forming operations. So again, this is again continuation. So elongation. So uniform elongation is desirable for good formability. Then at necking, true strain equals strain hardening exponent. So the condition is that thus high N value indicates large uniform elongation. Large strain hardening, the sheet which is having large strain hardening coefficient, it will have good or uniform elongation. So another one is at necking. Then in the case again at the necks, so localized or diffuse depending on strain rain sensitivity M of the material. The higher the value of the M, the more diffuse the necking becomes. The higher the value of M, the more diffuse the necking becomes. So you can see in the previous slide, N and M has to be controlled. We have seen it. So these are the areas where N and M you have to control. Next term is called yield point elongation. That is, after materials yield, the sheet stretches farther in certain regions without any increase in the lower yield point, while the other regions have not yielded. Okay. So if it is not happening, you can see on the sheet metal certain areas they will have certain scratch mark or appearance will be there on the sheet. In between there are certain areas where there will not be no stretch marks, or there will not be no marks or no evidence that a load has been affected on the sheet. So this stretch marks, whatever you are seeing on the sheet, they are called as Luder's band, or also called as strain marks. So Luder's band, it is elongated depressions on sheet surface, that is occurring because the sheet stretches further in certain regions without any increase in lower yield point. So between your lower yield point and upper yield point, the elongation has happened. So to avoid these marks, eliminate or reduce yield point elongation, or reduce the thickness of the sheet by 0.5 to 1.5 percentage by cold rolling. So you can ensure that the Luder's band will not be present on the sheet surface. So we can see that the reason is given as the yield point elongation. After material yields, the sheet stretches further in certain regions without any increase in the lower yield point. So only certain areas in the sheet only will be going for yielding. Other areas there will not be no yields, you will be able to see or visualize it. That is called as a Luder's band or strain marks on the sheet. Next is anisotropy. We have discussed it. One is called crystallographic anisotropy, preferred orientation of the grains. Next is mechanical fibering, alignment of impurities, inclusions and voids throughout the thickness of the sheet. Grain size also we have discussed. The coarser the grain, the rougher is the surface appearance. So as per ASTM, grain size of 7 or finer is preferred for general sheet metal forming operations. We will see some of these things in the next slide. So you can see this is a typical stress strain diagram. So you can see the material is yielded above your upper yield point. Then you can see to it, it is coming down into the lower yield point, and you can see it is continuously moving in that fashion. Okay, without any stress, only strain is happening, strain is increasing in the material, and thereafter it is yielding further. So when it is gone to the upper, when it comes to the lower, again the period which it is continuing in the lower condition, that is called as the yield point elongation. So you can see in the typical case over here, these are the areas where actually the strain is happening. These are the areas actually unyielded metals are present. So in the unyielded metals, you will not be able to see any marks. This will be pure perfect as like this. So these areas which is colored in blue or green or violet in section, there you can see there will be stretch marks can be seen on the material, that is called as the Luder's band. So you can see over here, this is the area where no yielding has been taken place. This is the area, these two are the areas where yielding is taken place. So these two are called as Luder's band. You can see clearly over here. So this is the area, this is the stretch marks which you can see on the material. Similarly here also, these are the stretch marks which you can see on the material, that is called as Luder's band. So how to avoid it, that we have seen in the last slide. You can see a figure C is also shown over here. C is the stretcher strains at the bottom of a steel can for household products, that normally you can able to visualize in your household products, whatever is there made from the steels, you can able to see the stretch marks will be there on the sheet. So these are things you need to avoid it. So for you have to conduct the formability test on the sheets to study about the various effects before the actual product is being tested up. So one of the important tests which normally every sheet metal will undergo, that is called as cupping test. It is also known as Ericsson cupping test. What you will do is that you have a die, you have a punch and a blank holder is that. In between you will keep your blank perfectly holded in between your die and your blank holder. You will move the punch down. Okay, when you move the punch down, you can see this is a step 1, step 2. Likewise, if you are continuously loading your punch, you can see at some point the material will completely deform. That is, this is also called as bulge test. So bulging, further bulging, you can see to that it will break at some point. So you can understand that you can able to get the dimensions of that, and you can able to understand that up to that point you can able to load the material easily. So figure A, so a cupping test for Ericsson test to determine the formability of metal. B is a bulge test results on steel sheets on various width. Okay, the specimen farthest left is subject to basically a simple tension. The specimen farthest right is subjected to equal biaxial stretching. Okay, so you can see still the material get deformed and finally it will break. To that point you will load the material so that you can able to understand what is the formability of the sheet you have been studying. You can able to determine. So the next one, I'll just run a small video so you will be able to understand how this Ericsson cup test is being performed. So you can see this is a typical Ericsson cup tester where you are keeping the sheet in its gripping position. You are rotating the handle, ensure that the sheet is gripped in between the anvils properly. Now you are setting the needle to 0. You are adjusting the scales. You have a rotary scale and you have a linear scale. You are adjusting it. Ensure the sheet is perfectly fixed. Now you can see on the other end you can provide a camera. So on that you can see the sheet is, you are exerting force with the help of a punch on the sheet. You are further doing it, the cupping is taking place and you can see to it, now it is cracked. So when it is cracked you have to stop it at that point. You can see that how much force based on the rotations you have given, how much force you have been given to the sheet. Okay, so what is the formability of that particular sheet of that particular dimension you can able to determine. So you can see over here, so it is extending and a fracture has happened here. So from the center to this distance, how much it has moved further you can able to determine. Okay, so you can remove the specimen, the fractured specimen, you can take it out. Okay, from the calculations you will be able to know how much force can be exerted on that particular material. So you can see whether the 3 stages is shown over here, where the deformation is going to start, and the final fracture is also shown over there. So a little more detailed study from a machine manufacturer, that also I'll run it to you, so you can have a clear understanding how and what is basically happening over here. So this is a typical machine on which the formability test on the sheet is performed. Okay, you will have the options to test various tests on the sheets. We will see from the video and we will discuss it one by one. So you can see on a 2D condition like this, so it is shown over here. So you can see this is particularly the blank, the blue color indicates your blank. This is your punch or the indenter, and you can see this is the top part, these are the blank holders. In between the blank is gripped properly. So you will move the indenter up. So as you can see, as you are moving the indenter up, the sheet will be deformed. You will be going to the condition where actually the sheet breaks like this. So that is the point at which that point you can able to calibrate and you can say that what is the formability of that particular sheet is. that kind of testing procedure that is normally called as Ericsson or Ericsson test or Ericsson or cupping test or Ericsson cup test. So you can see the indenter moves out, the material fails. So that is the upper drawing die is marked, specimen of the sheet metal is shown, lower drawing die is also shown. So these are the major components in the equipment. So clamping force you can able to determine. Yeah, the next kind of study what you are going to perform on the same machine, that is called the ear height or earring test, where you can see the sheet has been formed. You can see these edges are not uniform. So the non-uniform edges that is showing you as the earring over here. So how to see to it? So in that what you are doing is that instead of indenter it is completely deforming. You are deforming the sheet into a complete cup and studying how the earrings is going to, how the earring is going to come on your sheet. Will earring will present or will not the earring not present? That is called as earring test and the code is EN1669. So it is completely deformed. The sheet has been completely deformed. So drawing punch you are using, that is the upper drawing die. That is the upper drawing die and specimen of the sheet metal is shown. So there you can see the drawing die is held. Okay, held. Now you remember the shape of this and try to see what kind of a fitting or assembly is this shape belongs to in the case of die holding assemblies. Lower drawing die, clamping force, next is to test the determination of deformation of metal sheet in X and Y direction. Okay, so X and Y direction you are testing it. So the information what you are obtaining from this sheet will use to calculate or will use to understand the forming limit diagram of a particular sheet is. I'll come into the next slide, so I'll clearly explain you how that has been drawn for the various materials. Yeah, the next one of the sheet that is called as hydraulic formability of sheet. Instead of using a punch, what you are doing is that the sheet is being formed, okay, with the help of a hydraulic liquid. So inside this area you will be filling the hydraulic liquid and you can see that the assembly will move towards to the side and the material will get deformed into the die shape. And finally you can see as shown like this. Okay, so the material is going to fail. So you can ensure that under hydraulic forces or tension how much the load the sheet is going to carry out. You can see the deformation is happening, the sheet is stretching and the liquid has been and the sheet has been teared off, liquid has been came out through the opening. Upper drawing die, specimen, everything is shown to you. So these are the common tests which normally you will carry it out on the sheet metal operations. Yeah, so we have discussed, we have the cupping test, other things are easily visible over there. So I am not going to any descriptions of further of those tests. So the test which is important, the another important test which you have to carry out on the sheet is called forming limit diagram. It is called FLD. So in that case, this is done for various experimentations. So what is done is that sheet is marked with a grid pattern of circles 2.5 centimeter to 2.5 to 5 mm dia. So likewise, this is a circle before stretching. Same way, this is also, you can see here, this is after stretch. So two circles you will be drawing on the sheet and you are stretching it. When you are stretching the circle will be changed into the shape of ellipse. And you can see to it when this between this 2.5 and 5, you can see initially there was a wall thickness of somewhere around 1.25 mm will be existing on one side. As you are loading it, the outside shape will change into the ellipse, inside also, but certain condition you can see the wall thickness will become negligible and material will fail. So as in that case, you will have any changing into ellipse, you can see there will be a major axis will be there and a minor axis will be there. So the major axis we call it as major strain, positive direction is shown, and this is a major strain, this is a minor strain, positive. So major axis and minor axis is required. So continuously you will be testing this on various thickness sheets, etc., and you will be able to plot that on a sheet between your major strain and minor strain. That will give the information about forming limit diagram FLD. That is, sheet is marked with grid pattern of circles 2.5 to 5 mm dia. Blank is stretched over a punch and the deformation of circle is observed and measured in a regions where necking and the tears has been happened. Tearing has occurred. To develop unequal stretching, specimens are cut into various width. Square specimens produce equal biaxial stretching. Narrow specimen approaches a state of uniaxial stretching. So after a series of such tests is performed at different widths, okay, FLD is showing the boundaries between failure and safe region you are constructing. Okay, so after constructing, I'll come back to this slide. You can see over here, this is our initial cases, but it is still elongated. So when it is completely elongated, you can see now by this condition, the fracture would have been happened. When it gone to this condition, definitely the fracture would have been gone. So this is a before stretching condition and this is the after stretching condition. So you can see over here, these are the areas where actually the failure zones. Okay, these are the areas of pure shear and these are the areas of safe zone. So between a safe zone and a failure zone, how the material is going to behave. Don't confuse about the various lines. Various lines are drawn for various materials. So low carbon steel, aluminum alloy, how are they are going to fail, and what is the safe limit of operation which you can able to perform the task. So that information you can obtain from the forming limit diagram. Okay, so you can see forming limit diagram of various sheet metals. Although the major strain is always positive stretching, the minor strain may be either positive or negative. So in the lowest left of the diagram, R is the normal anisotropy of the sheet. Okay, so R is the normal anisotropy of the sheet, and the source is also shown there where the paper has been taken. So we'll go back to the previous slide. So data obtained from the different locations in each of the samples shown in that previous diagram. So higher the curve, the better the formability of the material. So that is the importance. The higher the curve, the better the formability of the material. A compressive minor strain is associated with a higher major strain than is a tensile minor strain of the same magnitude. The thicker the sheet, the higher the formability curve and more formable it is. So two information, the thicker the sheet, the higher its formability curve and sheet is more formable, and higher the curve, the better the formability of the material. So you can once again you can view it in the diagram over here. Okay, so you can see the higher sides of the curve. You can see this is a plane strain condition is given. You will study more about the plane strain etc. in the mechanics of solid. So I am not going to load those things in the manufacturing subject here. You will have time to study it. For understanding, this is how the formability limit diagrams is drawn, and these are the areas where failure is happening. These are the safer sites. So according to that condition, so thickness is a parameter. Based on the thickness, the curve is going to vary, we have seen. So accordingly, you can choose the different materials for deforming or forming operations. So the deformation and tearing in a sheet metal during formation is shown over here. You can see to the Luder's band also applied over here in the sheets. So these all things are practically will happen on the sheet. So you have to avoid as minimum as possible. So if we talk about finally, we have seen about the defects, but how it looks like is shown over here. This is called as wrinkling on the flange. Okay, so wrinkling in the wall is also shown over here. Okay, wrinkling in the wall is shown over here. C is the tearing one. You can see the sheet is teared off completely. So wrinkling in flange occurs due to the compressive buckling in the circumferential direction. Blank holding force should be sufficient to prevent buckling from occurrence. So proper clamping force is required, that you can study in the Ericsson cup test. Is the clamping force is sufficient enough? If you vary the clamping force over there, you can see these kinds of wrinkles may occur in the flange or may occur on the walls. Here flange is not present, so sometimes it may occur in the wall also. So wrinkling in the wall takes place when a wrinkled flange is drawn into the cup. If the clearance is very large, okay, the clearance between die and punch, if it is very large, a large suspended and unsupported region is there, which actually causes the wrinkling in the wall. Tearing occurring because of high tensile stresses that cause thinning and failure of the metal in the cup wall. Tearing can also occur in drawing process if the die has sharp corner radius. If the die has a sharp corner radius, tearing will occur in the case of sheets too. So these all things has to be taken care. The other two defects, D is called the earrings. I have already shown this. You can see the wavy shape of your outer edges, that is called as the earring. Occurs when the material is anisotropic. It has varying properties in different directions. And sometimes you can see the surface scratches are also visible. So surface scratches can be seen on the drawn part if the punch and die are not smooth or if the lubrications are not proper. So initially I told you the formability of sheet will depends on the properties of the sheet. We have discussed. Then we have seen the issues with the lubricants. These are the issues. These all are the issues. And the third one also we have discussed, that is if your die or punch is not smooth enough. If your die or punch or the clearance is not provided, you can see the earrings or surface scratches, or you can see the wrinkles may happen on the sheet. So these are the common defects which you can come across on the sheet. To understand or to test it, you have to go for the formability testing procedures. So next is bendability. Here also you can see, like forming, bendability of the sheet also needs to be tested. You can see sometimes when the sheet is going to bend, you can see the cracks may present on the sheet on the bendable edges. So this has to be avoided. So bendability test also you need to perform. So three figure A, B and C. A is tensile reduction of area, ductility. Okay, as ductility increases, bendability increases. The edge condition of the sheet, bendability decreases as edge roughness increases. Okay, You can see the elongated stretch marks you can see over here. The edge condition of the sheet, bendability decreases as edge roughness increases. The amount of shape and hardness of inclusions present in the sheet metal also will reduce the bendability of the sheet. So these are the things which you have to take care when you are performing the bending operations. So this is an example of a can manufacture. Okay, you can see the various steps which are involved over here. Starting from the blanking, you have deep drawing, redrawing, ironing, doming, okay, doming, necking and seaming. So these are the steps which are involved in a can manufacture. And if your thickness is of the size of, if your thickness is at least 50 percentage, or if you are drawing more than thickness than 50 percentage of your diameter or large, we call it as deep drawing operation. Okay, so that is how normally the shapes or the things are being made on the sheet. Okay, so drawing, deep drawing, redrawing, ironing, doming, necking, seaming, etc. You can see on the ironing and all, an ironing ring is provided over here. So the bottom shape you can see thickness etc. is being adjusted with the help of the ironing operation. Doming, this shape you are obtaining with the help of doming dies. You can see the various die and punch configuration which are used out. This may kept as a series or on parallel. That is what sir has explained you in the last class about the die punch combinations. Okay, so how you are keeping it, based on that the die punch combinations are going to change. With that, I will wind up my presentation. Thank you. Any doubt is there, we will discuss in the coming class. Okay, so that will be the end of the metal forming class. Once again, thank you all.